Hey folks, today's talk or lecture is going to be about spanning trees. There's actually some famous algorithms that we're going to look at in terms of locating spanning trees. I just prepared a relatively large, complex looking graph, but this is just random, right? It doesn't represent anything in particular. I just wanted to give you first an idea of what a spanning tree is, and then we'll talk about weighted graphs and finding minimum cost spanning trees. So the first thing is, this graph has 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 nodes. A spanning tree is a subgraph, so it'll contain all of these nodes. So that's what makes it spanning, right? It'll be a graph that spans the vertices of the graph we've got here, but it'll be a tree. And its edges will come out of the nodes that, or excuse me, the edges that we're seeing here. So probably a picture is worth 1,000 words. This node here on the end is a leaf in the original tree. Well, I guess it's not a leaf because it's not necessarily a tree, but we're definitely going to need to have that connection in a tree that covers these vertices to be connected, right? If it didn't have this edge, then we'd have a disconnected thing if it included all the vertices. And then you're free to do pretty much whatever you want, I think, with the rest of these guys. For instance, I guess I could do that, and maybe I want to come up here and grab him. Let me go down there to that one. Let's keep going and get this guy. Let's make it kind of have a spine there so we can get some other things off of that spine. And what else? I already made it to that node. Well, I got to get to him somehow, and I got to get to him somehow. So you kind of saw how you think about growing a tree to cover all the nodes of the graph. Just make sure that you don't ever produce any cycles, and you're sort of guaranteed to get a tree. The other thing we know, of course, is theoretical. How many edges should there be in this tree? I did count it before, and I believe I got 13 for the vertices. 6, 7, 8, 9, 10, 11. Yeah, 13. So there ought to be 12 edges in this. Did we, in fact, get 12? 1, 2, 3, 4. Let me just go across the top. 6, 7, 8, 9, 10. Oh, I forgot these. 11 and 12. Okay, so yeah, we've got a tree. It's connected, there's no cycles, it's got the right number of edges, it must be good. There was a lot of freedom, though, in what I just did. I could have approached it multiple different ways. For instance, you could have made the spine go all the way up along the top. Heck, you could make the spine kind of go all the way around the perimeter of the thing, just stopping short of reconnecting up. Don't make a cycle, and then use whatever you want to get the few edges that are in the interior. Keep saying edges when I mean vertices. Yeah, anyway, yeah. So lots and lots of different spanning trees. In fact, that's sort of an interesting question. How many different spanning trees are there for a particular graph? Generally speaking, so many that you don't even want to try to count them. Right? If you're, well, maybe not on this one. There's probably only a couple of hundred spanning trees on this graph. But on a graph of any appreciable size, the kind of things that you'd really see in industrial or research settings, hundreds of vertices and, Googleplex worth of spanning trees, probably, maybe more, huge numbers. So I just restored the graph to its original state, and also I put some numbers on each of the edges. The problem we're going to look at next is done in this sort of setting. It's called a weighted graph. Basically, this came up originally as a practical problem. AT&T research people worked on this pretty hard back in the 40s and 50s. You see, AT&T, I'm talking about the era of old school, like copper wire being used to transmit signals, right? So they would lay in trunks of cables between different locations, and then from these locations they could distribute stuff to homes and businesses. But these big connections, these expensive connections between central stations, they they were problematic. You had to lay big piles of cable, and we're talking like 6-inch diameter, packed with twisted pairs of copper wire. They were expensive, and so the point of looking at a graph like this is these numbers might tell you how much it's going to cost to lay the cable between certain cities, probably in millions of dollars. All right. So what AT&T wants to do is not spend all this money, right? They don't want to put a full connection on the graph. What they want to do minimally is get a tree. If they could just find a tree in here that somehow was the least expensive, they know it'd be possible to pass messages around, right? If you have somebody here who wants to talk to somebody here, if you've got a tree, there is a route that goes between the edges of that tree that gets there. Now, to be quite honest, they wouldn't go with that entirely. The real problem would be to develop what's called a minimal two-connected graph, which would mean that even if some trunk line was down, it'd be possible to send a message from any place to any other place. With a tree, you could have certain lines that, certain of the edges, if they're out of service, it would break everything. You wouldn't want to have that in a resilient network. So they looked truthfully for two connected graphs, but that's a much harder problem, and we can see the algorithms pretty nicely for merely trees. So that's what we're going to look at. All right, so two different researchers came up independently with algorithms that work to solve this problem. Let's see, the names are Kruskal and Prim, and I always forget who's who. I think it was Gene Kruskal, and I'm going to check. Sorry, nobody's named Gene. Joseph Kruskal, I should be able to remember that one for some reason, and Robert Prim. These guys, one of them worked at AT&T, the other didn't, but they were both working on this question of finding an algorithm for calculating a spanning tree that has the least total cost. Actually, both of the algorithms they developed are in a category, I don't believe they called it this at the time, but what we now call them greedy algorithms. And greedy algorithms, when they exist, are usually, well, they're easy to implement, and it's kind of cool if you can show that a greedy algorithm will do the trick, that you know that this sort of problem is solvable. Maybe it's not efficient, but at least it's solvable. So what is a greedy algorithm? Well, I think Kruskal's algorithm is a great example of a greedy algorithm. Somewhere amongst all these numbers is the cheapest edge, isn't there? Can we find it? If you wanted, I could go and sort the list of edges, but I found it. It's this 11, isn't it? So what Kruskal's algorithm says is find the cheapest edge and start by making that edge and its endpoints a part of your graph. Now be greedy. Go for the next best thing. Find the next cheapest edge. So see why you might call it greedy? You're trying to just do the best thing possible. Find the very cheapest edge you could. Make that part of your tree. What is next cheapest after that 11? I'm seeing a 17 over there. So add that. Now, I think so far nothing could have gone wrong, but there does come a time when you think, I'd really like to add this next edge, but if I did, I wouldn't have a tree. So you have to spell that out fairly carefully in a greedy algorithm. What's a condition that allows you to grab the very next cheapest thing? And for us, it's that the graph needs to remain a tree. So we'll greedily add edges unless they would form a circuit. So that's actually what Kruskal's algorithm is as a high-level description. It's greedy selection of edges with a proviso. Edges that don't create circuits. Probably the best way to implement Kruskal's algorithm is first sort all the edges and see which one is cheapest and which one is cheapest after that. But I think this example is small enough that we may be able to get away with just doing it. Do you guys see what's the next cheapest edge out here? We've taken care of the two that were in the teens. So the next cheap guy should be somewhere in the 20s. Well, that's 49, 50, 23 is pretty good. Oop, there's a 21. 21's my new best choice. Wow, there's a lot of 23s. But anyway, 21 is good. Let's add 21. All right. So far, so good. Now, could I add any of the 23s that I wanted to? There's a bunch of them. It might be that one of them would cause a circuit, so don't do it. It might be that there's different ways that you could add the 23s. In this one, we lucked out. All the 23s are just going to be fine. That's the next cheapest category, so let's throw them in. Wow, that's kind of neat. I've got this long, snaky thing. That is not normally how it all works out. But did you see that I started with something totally disjoint, two edges that were completely separated from another. Then we had this one that was two edges, and then that one separate. But by adding the 23s, it sort of globbed things together. What's the next cheapest after this? I'm thinking this 24 is looking pretty cheap. I believe that's it, yeah. So that's the next edge to add in. Definitely getting a very tree-like looking thing now. After 24, I don't see any 25s. There's a 26 up here. Let's put it in. And then, so far I haven't had any concerns. It didn't look like any of these edges we added would have caused a circuit. If it had caused a circuit, I'd have stopped and not used it. But they were all fine. But the next one I think is problematic. If I put in this 27, that is the next cheapest edge, right, after the 26. There's no 26.5s in here, right? So if I were to put that in, what would happen? We'd get a circuit that went like that. So we're not going to add that 27. But we're not done yet because there's still nodes that haven't been used, right? So we're going to need to keep adding stuff. But I think we're done with the 20s. Are there any other nodes or edges of weight in the 20s that we might use? I don't see them. So what's the next cheapest? Well, 30. Should I put 30 in? Hell no. There's a triangle, right? So that's going to cause a circuit. 31. Oh, that's looking kind of, oh no. There's a bigger circuit here that if I added that 31, I would close that up. Oh, there's another 31. Can I add it? It doesn't form any circuits, so yeah. That's brilliant. So what about next up? Next up is 32. I can add this edge without creating a circuit. So I do. And then I have to deal with Maine and Hawaii, or remote locations that have only a couple of ways to get there. So I'm going to skip. Well, maybe I shouldn't skip. We just got to past 32. What's next in weight after 32? Are there really no other 30s? I wasn't very random when I did these numbers. So no more things in the 30s. How about the 40s? There's a 40, but we can't put it in. It would form a circuit. 48? Nah, sorry. That would make a circuit too, right? There'd be a triangle right there. 40, I think we're done with the 40s. The 50. That makes a triangle right there. We shouldn't add it. 50, and then I think I've either crossed things out or used them for most of these edges. 56. Should we add that? No, see this big house-shaped thing? That's a circuit. So we don't add 56. Oh, I skipped 49. I missed it. 49 we should have added, and that's when we finally get this remote node as a part of our tree. All right, past 56, I think the next thing available to us is in the 60s. And there it is, 64. Well, I'm not supposed to be circling those. Circle the node at the other end of it. I must be done. I must be done. How do I know I'm done? Well, one of the things you always want to make sure you're doing with an algorithm is clearly defining a criterion for when you stop. Right? When are you going to be finished? And you know ahead of time for all these algorithms when you're going to be done. You're trying to pick n-1 edges out of this graph. The graph had 13 nodes, so n-1 is 12. As soon as I got to a count of 12 of the edges that we've used, I should stop. Did I actually get to 12 just now? I mean, I'm not going to count them up in the order we added them, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That was the 12th edge to add, so that's when we know we can stop. We're finished. So it's interesting to try to convince yourself that this algorithm will definitely find you the cheapest spanning tree, the minimal cost spanning tree. But you know, at every stage, if one of the decisions we'd made had gone some other way, we'd end up with something that had a slightly higher cost. I mean, if, for instance, I don't know, how about this 23 right here? If I didn't use that edge, then I would still need to make sure there was connections between these two sort of groups of things, the things up to the upper right and the things down to the lower left. How could I make that happen? Well, I would have had to use something more expensive to do it. So it's an interesting point. I think that's a compelling argument, but I'm wondering what a good rigorous proof of this would look like. Probably it would be best proved by induction. You know, suppose this algorithm works on a graph with n nodes. Can you show that it will work on a graph with n+1 nodes? All right, so that was the algorithm that Joseph Kruskal discovered for coming up with the minimal spanning tree covering a weighted graph. Then we'll look at Robert Prim's algorithm. And like Kruskal's, this is a greedy algorithm, but the emphasis is different. What goes on in Prim's algorithm is that you grow the tree in a greedy fashion. Well, maintaining that it's a connected graph at all time. So, maintain connectivity. If you notice, when we did Kruskal's algorithm, you don't necessarily have a connected graph at any time. And certainly finally the last step, because you know that you've got n-1 edges at that point. But in Prim's algorithm, you keep the graph that you're building connected. Well, maintaining connect, let's change that into connectivity. Right, so you'll have a graph that stays connected and it's going to grow out. Actually, this is rather like the way real organic, vegetable matter things grow. Trees grow in a way that they take the path of least resistance. If a tree is trying to grow up through one of those squares they put in the sidewalks, and eventually its roots start to run into concrete, the roots that run into concrete stop progressing, but the ones that find a crack keep going, and they make the crack bigger, and then they split it eventually. So that's the kind of idea you have here. Is the tree is going to grow outward. At each stage, it's always going to take the biggest. Well, I shouldn't say biggest profit. It's going to take the smallest path outward. So it's a little strange in that you have to look at the entire tree you've built so far and consider all the ways to go out from it, and then take the least amongst them. Let's put it in action and see how it proceeds. One thing about Prim's algorithm is it matters where you start. You may get different results if you have different starting points. So where should I pick as a starting point? I mean, it's arbitrary because I know that every node eventually is going to be part of this minimal weight spanning tree, but I want one that's going to illustrate things nicely. So I don't know. Here, I'll take this guy in the middle. So we'll start with a single node, and then we're going to grow outward from that node in the cheapest possible fashion. Great, I have two choices. I can go out this 23 or out that 23. So pick one. If there's choices, you pick one. How about we go this way? All right, so at this stage, as this is stage 2 of the algorithm, my tree consists of these two nodes and the edge between them. It's a path of length 1. And we look at that entire thing, look it over, and see where is the cheapest edge leaving it. Looks like, to me, it's this 21 here. We've got a 40, 23, 48, 56, 30. Yeah, it's that 21. So we next follow that one out to its endpoint. So the tree we've constructed so far is isomorphic to a path of length 2. What's the cheapest way out of that path of length 2? I got a 23 over here. I already used that. Oh, that 21 is already part of the tree. These guys, nah. They don't beat the 23. Oh, 19. 19's looking like it. So we follow that guy and capture its endpoint. So it looks like, so far, like the graph that I'm drawing just keeps growing off the end. And actually, often that's the way we think of things growing. They progress off the end, like the tree branches go higher, and then the branches branch, and then the branches branch, etc. But that is not necessarily the way it all works, and I think we're going to see an example of that next. If I were to continue growing off the end, this 23 would be the best. But there are other options. For instance, I could take that 23 off the other end of it, but there's something even better. Right here is a 17 that we should use, right? So that's, in fact, the cheapest way out of this graph now, or away from this tree. And now we see as the other proviso that Prim you have to put into the algorithm. You would never want to pick an edge that came back to yourself. You're not going to turn around and grow into your own trunk as a tree, right? So this 23 here, that's illegal. We wouldn't go from this tree to itself. We're going to grow the tree always in a direction where it goes from what we've built so far to the rest of the graph, never back to ourselves. So we're not going to do that one. So out of this tree that I've built thus far, what is the cheapest way out? It can't be that 23. That doesn't leave the tree. 31? No, that's a pretty high number. There's a 24 here. 20, 56, 48, 23s. That's our new loci, isn't it? That's the cheapest way to go from the tree so far to the rest of the graph. Great. And now we just reached the point where we've got that access to that 11. I know that's going to go in because that's the cheapest edge in the whole graph, right? So we get there. All right, are we done yet? No, there's still a few nodes that haven't been put into the tree, so we're not finished. What is the ending criterion for this? In this case, it's kind of a simplistic ending criterion. You grow the tree until you're finished. If there are no other nodes that you could grow towards, it's impossible to continue this. So, all right, well, we've got this convoluted looking bit here. What is the cheapest edge that goes from green to one of the black nodes? I guess I try to be systematic and go around here 31, 50, 31. 27 would not be legal because it goes between two green nodes. 24, that's good. Is that the lowest I've seen thus far? Yeah. 30, 56, nope, not 48, that goes to a green node. Certainly not 64 or 97. 26, ooh, I think that's a new low. Yeah. So that's the cheapest way to expand the graph out from there. All right, we don't have too many edges, or rather nodes left to get to, so we can start looking at, I know I'm not gonna have to look at this one yet because I gotta get here first, right? But 50, 31, 24, 30, 56, 32, 64, 97. I think the least value I heard in all of that was a 31. So there you go. Oh well, what's left? Now we're looking for the cheapest edge, leaving the green, heading towards the black. So 49, ooh, 24, 30, 56, 32, 64, 97. These are all, I think it's at 24. There's only 3 nodes left to look at expanding towards. So is it some way to get to this one? There's only one way to get to this one, and it's a 49. That's pretty large. There's a 32 that takes me down to that one. That's probably our best bet at this stage. Yep, 32. And finally, we get to use the 49 here because the other guy has 64 and 97 connected to it. And last is this edge connecting us out to there. Okay, so that's Prim's algorithm in action. I'm going to go display some of this stuff on the screen on my screencast setup, and we'll talk more about some of the consequences and try to give you a better, more formal description of the algorithms. Okay, so here's a scan of the chapter in the book that we're working on. It's 10.6, titled Spanning Trees and a Shortest Path Algorithm. I'll just mention that we are going to be doing Dijkstra's algorithm, the shortest path algorithm they're talking about, on Wednesday. So for today, it's just spanning trees. And here's the definition. I think I said this, but just speaking it maybe wasn't the best. So here it is in writing. A spanning tree for a graph G is a subgraph of G that contains every vertex of G and is a tree. Okay, that makes sense. A couple of nice little points are made in this next thing. They call it just a proposition, so not quite powerful enough to be a theorem. Can I get a little bigger on that to make sure we can all see it? So first of all, if you've got a connected graph, there is a spanning tree. It's just claiming the existence. Every connected graph has a spanning tree. And then any 2 spanning trees for a graph have the same number of edges. Well, the second one is clear, I think, because whatever the number of nodes in the graph is, the number of edges in a tree that has all those nodes is going to be 1 fewer, n-1. So just the issue that it's always possible to find a spanning tree, provided you've got a connected graph. That's useful. I'm not going to go through the proof of this, but it's pretty straightforward, and you should make sure that you believe it. They do have a nice example here where you just see a couple of examples of spanning trees. So you've got this graph. It's only got 1 circuit in it, so it's close to being a tree already. And you see that the 1 circuit can be broken in 3 different ways. You can take out that edge that's on a sort of diagonal. You can take out the bottom edge, or you can take out the edge that runs vertically. So on to minimal spanning trees. And they give an example made up about airlines, and airlines typically don't do interesting tree structures in their flight routes. The reason is it's cheaper for the airline usually to find a good deal in renting space and having places to store the aircraft, etc., at a single hub. A large airport that specializes in being a hub. Chicago is one. Actually, Detroit is a hub too, I think. I'm not sure about some of these other ones. I used to live in Chicago, so I know that both of their airports are considered hubs there. Anyway, you run your operations so that you've got a star tree with a hub at the middle, and all your connections go to other things. That's probably not the most efficient in terms of fuel or personnel, but it's the most efficient in terms of just overall cost. So that example is probably not the best one to use, but anyway, what do we need to do to understand this minimal spanning tree business? First of all, we need the definition of a weighted graph. I think that's pretty clear, but positive real numbers are assigned to every edge of a graph. That's what makes it a weighted graph. The ones I just did had integers. We could just consider that those were rounded off or something. But, the sum of the weights of all the edges is the total weight of the graph. That's an interesting thing. So that's the reason we want to know about the total weight is that's actually the thing we're minimizing when we find a minimum spanning tree. It's a spanning tree, a connected acyclic graph whose nodes cover all the graphs, all the original graphs nodes. If it has the least possible total weight, that's what makes it a minimum spanning tree. Okay, so here's Kruskal's algorithm actually spelled out in detail. Unfortunately, it breaks a page, but we'll deal. So our input is a connected weighted graph G with n vertices, and obviously n's got to be a positive integer. It's counting the number of vertices. Here's the body of the algorithm. We'll initialize T to have all the vertices of G and no edges. I usually think of this, frankly, differently. I think of it as you're adding in the edges, you're also adding in the endpoints of those edges. But it's fine to do it this way. You just think about all of T's vertices are in there. The graph is completely disconnected, right, since it has no edges. Let E be the set of all the edges of G, and let M equal 0, just initializing things. And here's the loop. Here's what we do. While M is less than n minus 1, which n minus 1 is the number of edges, right? Okay, so long as you haven't gotten to n minus 1, do this. Find an edge in E that has the least weight. Delete that edge from E because you're not going to add it in twice, right? So, and then if the addition of E to the edge set of T does not produce a circuit, then add E to the edge set of T. Okay, now we bump up M, set M to M minus 1, M plus 1, and then we are at the end of that little loop. This is where all the meat of the algorithm is happening. The rest of it was set up and talking about what are our input criteria. So it's this one loop that they're just, I'm not sure if I would use a while loop for this kind of construction. I'd say for I equals 1 to n minus 1, do it, but this is just pseudocode anyway, so it gives us the idea. You've got a loop structure where m is the incremented loop variable, and what you're told to do in there is locate the cheapest edge that hasn't been used so far. Take it out of the edge set E and add it to the edge set of T, provided you wouldn't make a circuit by doing that. Okay, so we've seen examples of the algorithm working. You can follow it through. A second example is in here. It's kind of a nice one. I am not covering this, but I really recommend to you guys to look at this theorem, which proves that is a proof that that Kruskal's algorithm is correct. Look at it carefully and convince yourself that it really does the job, that it indeed gives a compelling argument that the algorithm works. You've had enough experience now with reading and writing proofs that I think you should be able to get through this. Come prepared with questions for Monday's class. If there's elements of this proof that you didn't quite get, I want to hear your questions. All right, so Prim's algorithm is our next one. Recall, this is the one where you think about the graph growing out from an initial vertex out. There's a sort of ugly, distorted picture of Robert Prim there in the margin. It's fine looking in the book, it's just my scan makes it horrible. Anyway, Prim's algorithm. So what did we do there? It's the same input, and the algorithm body has this parenthetical remark in it. Build a subgraph T of G by starting with any vertex V of G and attaching edges with their endpoints, one by one, to an as yet unconnected vertex of G, each time choosing an edge of least weight that is adjacent to a vertex of T. That says it. Let's see how they make it programmatic or pseudocode it. So the first step, pick a vertex. Just randomly choose a vertex V of G and let T be the graph with one vertex and no edges. Cool. So that's your initial condition. You've got a tree that's got a single vertex in it. Let V be the set of all edges of G except for that one. All right, so V is going to be the things to which we will look for connections, and T, right now it's just a single node, but T is the graph that we're building, so we're going to go from T to V. Right? Here they are using a for loop. I don't know why they did a while in the previous one and a for in this one. Oh, maybe I do. Yeah, maybe it's conceptually easier to think. It doesn't matter. For I from 1 to n minus 1, we're going to take n, they're absolutely n minus 1 steps, so this is nice. You know that it's going to finish rapidly. You find an edge E of G such that, okay, there's two conditions. One, I wish they had laid this out as a list or something. But condition one is that E connects T to one of the vertices, to some one of the vertices in V. And two, it's the cheapest one. E has the least weight of all edges connecting T to a vertex in V. So you're sort of thinking about the graph divided into two parts. T that you've built so far, and the V, which is things that remain to be connected to. And you're looking for all the connections between those two parts, and amongst them find the cheapest one. So that'll amount to finding a whole bunch of edges that satisfy that condition. They go from T to V, sorting that list, finding the least weight thing in it. All right. So if they're saying let W be the endpoint of E that is in V, right? So you're going to add E and W to the edge and vertex sets of T respectively, and then delete W from V. That's important. You don't want to ever consider going to W again. It's been added into T. And then once you've finished these n minus 1 steps, you're done. T will be a minimal spanning tree. How do you know? It's going to have n minus 1 edges. You took n minus 1 steps, and in each step you added an edge. And you never created a loop, did you? You couldn't have possibly, I shouldn't say loop, you never created a circuit, because you are always going from T to a disjoint set. The only way you could have created a loop or a circuit could only be created by going from T back to itself. And the construction here prevents us from doing that. So those are the algorithms. There's also a proof in here for the correctness of Prim's algorithm. Same deal. I'd like you to analyze this, make sure you believe it, and come with questions about this argument on Monday. So there's another example here. This is talking about kind of comparing the two things. You'll notice that what they're showing here is Kruskal's algorithm results in one graph, and Prim's algorithm results in a different graph. The trees look different. They have the same weight, though. So, in fact, there's two distinct minimum spanning trees for this particular graph. Technically, if there's a lot of edges that are tied, that have the same weight, you're going to have choices to make in both algorithms, which edge to use. So, every time you get a choice, you up the number of potential minimum weight spanning trees. Okay, so the rest of this is Dijkstra's algorithm. That is a Dutch spelling, so it's pronounced Dijkstra. We were going to talk about that on Wednesday, so for today we are finished. And hope you enjoy the remainder of your weekend.